Welcome to DfAM and Export Training. My name is Sunatasha Singhara, and I am an Associate Onboarding Engineer at Entopology, and I'll be leading this training today on design for additive manufacturing. If you haven't already, please download the files that is linked in this training description. You'll have access to this PowerPoint slide I have up as your reference as a PDF file. And all those files, the NTOP files that you'll be seeing today are in there as well for your resources. So today's training will be split into 4 different sections based on the different considerations for additive manufacturing. And so we'll be going over things like the initial concept or design, elements to consider when creating a design for additive manufacturing, such as self-supporting structures. We'll be looking at a few different lattice structures that are self-supporting, as well as how to create those escape holes for things like powder-based additive manufacturing methods, as well as looking at an option to add an overhang constraint to your topology optimization if you're going to be trying to remove material from a design space. We'll also look at the different tools in NTOP to look at the best orientation for build prep and add those supports and a few custom blocks as well that we have to generate those supports for your parts. We'll also look at slicing. So if you want to directly take the slice data into your printer rather than having to first mesh the geometry, which is an extra step and can also create a very large file. We can do that in NTOP and then export to some of the partner machines. But we will also be going over those meshing techniques as well if you do want to go through that part of meshing the geometry and take your part out as, for example, an STL mesh file. So we'll explore those options of how to choose the right mesh for that. So let's get started. And for this self-supporting structures, I'll show this file where we have a starting box that we want to add a lattice structure to. And so here, I'm just going to show you our lattice options that are self-supporting for when you're considering your design. So let's first look at this TPMS structure. So typically, the TPMS structures are self-supporting, given that you control the cell size. Like in this case, it's 4, 4, 4, so it has the same length with height. And generally, it would be self-supporting. But if you try to warp a structure like this, depending on how you change it or warp it, that might affect its ability to be self-supporting. So you would want to keep an eye on that if you're going to try to do something like warping or changing those structure that is already self-supporting in this way. So that's with the TPMS surface-based lattice. And with the graph lattice, so both of these are created from our periodic lattice body block, which can be found in the beta tab under lattices generate. And both of these are periodic lattices, as the block name suggests. For the graph lattice, let's isolate this. The 2 important elements to consider when thinking about creating self-supporting structures are the unit cell type, so the unit cell type and the cell size. So in general, a well-chosen and oriented lattice is self-supporting, but these are the key aspects to think about. So if I change this unit cell type to a simple cubic, you can see that this would not be self-supporting. Things like body-centered cubic, however, is self-supporting given that you control the cell size to make sure that it is oriented without those overhang angles that would need extra support structure. So the cell size is one thing, but also how you orient it in relation to the build plane as well. So even if you have the cell size that is in this way, self-supporting, if we rotate this and try to print it on a build plane in this orientation, then it would no longer be self-supporting. So all these things to consider. And with graph or beam lattices, if you are ever unsure whether it is self-supporting, we have tools in NTOP to help you kind of check that. So if we go to Beta's Hub lattices and utilities, there are options to filter beams based on length and angle. So if we go and take a look at this, I'm actually gonna isolate our Voronoi lattice as an example of how this filter by angle works. And we have defined that build plane that we're showing right now to be pointing upwards. So the build plate is right here, and also specified our overhang angle. And what we could do with this filtered by angle block is bring in that lattice body, give it a condition where we say, we are filtering anything that is, for example, in this case, greater than or equal to this overhang angle with respect to the build plane. So with respect to our build plate, that angle. And if we look at this filtered results, we can see that it is keeping those things that are meeting the condition and removing any beams that are less than that overhang angle. So if you filter your structure this way and get this result, this might not be, something that you'll end up using as your final result and bringing out and printing it. So it's just something you can play around with and use as one of your options. There are also other utilities as well. You can merge lattice bodies or extend open lattice body beams, collapsing lattice body vertices. So these are some of those options for you to have more control over your lattice design and structure. But what this filter beams by angle is really, really good for is to double check your structure. So to really making sure if we change this condition, so in this block right here, we have the condition in reverse to have the condition be less than or equal to the overhang angle. And if we isolate this, nothing shows up. And there's also this warning that says that this graph lattice contains no beams that are meeting this condition. This means that, so this graph lattice is from the one that we have up here with this self-supporting structure that we showed earlier. Then we can be sure with this warning, in this case, that's a good thing, that there are no beams that have that angle below our overhang angle that we specified. So with that, let's move on to the next thing, which I will show is how to create escape holes. So we have just this bracket, which we imported into NTOP and then converted to an implicit body, as well as shelled. So if we isolate the shell, let's take a look at the cross section. So it is a shelled part now. And we'll try to add an escape hole to ensure that we can remove powder from that powder-based additive manufacturing method or process. And you can think about this in a very simple way. So the simplest method to do this is just to add like a cylinder, put it where it overlaps with the shell, and then kind of subtract that cylinder away from this part to create that hole where the material is removed. And to do that, we can use this cylinder block. So this is something that we can grab from the Create tab. And there are two options for the cylinder. So one created from 2 points and one that's created from line segments, but they're very similar. It's just which elements you're using to base the cylinder off of. But for our cylinder, we created 1 point that is right here below our bottom face shell. And the second point, let's look here, right here. So the X and the Y positions, we just took from this part by going into the properties and into that bounding box to get the centroid. So this is one way to add a quick automation to your workflow by adding in that dependency. So we have those X and Y points specified, and then one of the points is just offsetted in the Z direction by 10 millimeters. And then we added a radius of 5 to the cylinder. So we created something like this that is overlapping with that part of the shell, and then Boolean subtracted away from it. So if we isolate this Boolean subtract block, we can see that we've now added that hole in very few simple steps. Now, if we want to add multiple holes on the same face, what we can do is first, if we think about our part and where exactly we want to have the holes, we know that we want the holes to be on just this one face. So what we're going to do is first create a random set of points on this face where we can create one cylinder and then repeat that one cylinder so that we are placing them multiple cylinders on the locations of those points. And to do this, we need to extract this space. So to do that, we, because the random points on mesh block requires a mesh as an input. So what we have to do, since we do have that CAD part, we can use a CAD face. So we selected from this, we isolate that CAD block, we selected the face and then made this into a CAD face variable by right-clicking it. And then we had this CAD face variable that we use as a reference in the mesh from CAD body to create a mesh out of it. And this mesh input that we use to create these random sets of points can be any kind of mesh. So it could be a list of CAD body that converted into mesh, so multiple faces even, or this mesh doesn't have to be flat like this one. In this case, we have a flat surface, but it can also contain curves. And this random point on mesh block will generate based on your given point count and the relaxation iteration, which controls how even the points are distributed, as well as the randomness here. And then if we look at this, it just created that set of points. And for this closest point block, I want to mention that for this part, this closest point block is giving us this normal. So later on, when we are creating holes, this is good if you're having a curvature to make sure that the holes that you're adding are normal, if you like them to be normal to your part. So we can use this closest point to access the normal of every single point on that list, as well as the distance. So this closest point brings that set of points to the body that we want. And if we look at the distance, we can see that the points that these closest points block produces actually didn't change the location from the random points on mesh because it is a flat surface. With that, we have this cylinder that we created. And this orient object block would be that block that allows us to put this cylinder on all the points that we've created. So what it needs is a source plane, as well as the destination planes, which we inputted as a list. So the source plane comes from this cylinder. So if we hover over this, it tells us that it is from that cylinder bounding box centroid. So this is the plane created with the block plane from normal. And then we brought in that bounding box centroid from the cylinder and used it as the origin. And then we're saying we're going to want to repeat the cylinders at all of these locations. So we brought in the points for holes as a list into the origins where we want to have these cylinders placed, as well as that normal information about the direction of that hole that we're wanting to create. So if we isolate this, these are a bunch of the cylinders that we created, and then just the same step again, Boolean subtracted that from the shell to get this perforated part. So that's kind of the workflow that you would go through to create either one or multiple escape holes for powder-based methods. Another thing I want to touch on is this topology optimization with overhang constraints. So we have in top the capability to add overhang constraints to your topology optimization when you're removing material from a part to try to get an optimized structure based on whatever load case you have. So in this constraint, you will add in the build direction to specify where you have your build plate, as well as add in that condition for your maximum overhang angle with respect to the build plate. And you would choose the areas of boundaries that you would want that to have. And then so if we just compare, if the result is unconstrained, and let's look at it from this view, we can see that it has some of those overhang angles. But if we look at the one with the constraint, the optimization kind of removed material a little bit differently and made sure that it will be possible to print this without adding supports. So this is just one of the features we have. Let's go back to that slide again. So we went through all of these initial concepts, so those considerations when designing a part. Now we're going to talk about when you're doing the build prep. So going into the orienting your part on a build plate and finding how to add the minimum amount of supports. So I'm going to go into this file, part orientation support, and all these files you have in the files that you've downloaded as well. We're starting with a simple sphere cube that you have already seen in core, and we added in a printer bounding box or that build volume. So in this case, we chose, if you go to the additive manufacturing, there are a few different build volumes based on the machine you have that you can choose from. And this is just a bounding box, right, to give us that kind of idea of the build volume, which means that if the machine that you have is not listed here, you can always create your own by just going to the search bar and then searching bounding box, and then giving it those dimensions that are relevant for your part, for your machine. And then also from that, we used a corner plane from box floor block, which you can grab from this build preparation. There's an option to do corner plane or centered plane from box 4, and the input would just be this bounding box, and it would give us this plane that we'll use as a reference in future steps. And so normally, if you have designed something with additive manufacturing in mind, you might already know how you would want to orient it on a build plane. But there are tools in NTOP for you to explore some other options, or even check your intuition on how to best orient your part on the build plate. So to do that, we have this block called minimum support orientation, which you can specify the body that you're trying to orient, as well as that build plane. and give it information like how much you want it to be offset from the build plate, or and the overhang angle, if you want support regions to be internal or external or all regions. And then it would run through a number of candidates, an algorithm that would figure out a few of the best orientations that would require the minimum amount of support structure. So if we click into the properties of this block, once the block has run, you can see a few different options here of the different possible orientations that would generate the amount of support structure. So to use information from this block, we can grab that transform object block, which takes in that object, the initial object, and then it will transform it based on whatever option you choose. So these are all indexed with 0, 1, 2, 3, 4. And using this list element block, you can extract an individual index as a transformation for this original sphere cube. So if we turn on the visibility of this, we see that we have created another kind of volume that is based on that one option of that best orientation. So I'm going to turn off the visibility of the original cube now. And now thinking about adding those support structures, in NTOP, you can start to roughly find out where that support is needed based on specified overhang angles. Anything below the overhang angle will have support added for this block. So this block is called the manufacturing support volume block. And you would put in the best orientation that we found earlier and the build plane, as well as the specifying the overhang angle and feature size. And let's see what it creates. So this creates a kind of voxel grid, which I like to imagine as sort of pixels where the supports would be needed. And we could use this as the initial baseline for creating our support structures in NTOP. So first, we'd have to convert it to an implicit body from voxel grid using this block to be able to use it. And we're going to use it as a basis to create the support structure. With this volume lattice block, you can create columns by choosing the unit type column that is specified here. And we are inputting this initial supports that was created from this manufacturing support volume block as the base body to generate a lattice. And this volume lattice, if we take, let's turn off this visibility and turn on this volume lattice, by changing the fill type to be all touching, it will cover a larger area outside of the initial volume as well. And then we just thicken it to add that volume and specify the size or the thickness of those beams. And then, but then we see here too that we have some parts that are going, if we highlight it, they're going all the way into our body, and there's some protruding out of the build plate as well. So it's just one final step of Boolean subtracting this columns using the best orientation, so this body and the build plate. And this gives us this structure that is trimmed to those two things. And so understanding this simple process of how this support structures can be created just from this first initial support volume discovery step and also that lattice column step is helpful in kind of figuring out how we can go on to create more workflows specifically for support structures that we can have even more control over. So what I'm going to show you next are a few of those more complex workflows packaged into custom blocks that we can see how it is able to give us more control over our support structure. So in this case, we have this custom block that takes in the part and the build plane and all these specified overhang angles. So wherever we have this overhang angle or less, we'd want to add those support structures too, as well as you can see here, it's tapered to the body. So these support structures are created in such a way that wherever you have this connection to the body, that this support would be thinner at that connection point and then gets larger as it gets to the column. And it has this vertical part and everything kind of goes into that normal direction to the body. So this custom block allows us to kind of have that control, more control over those support structures. So let's take a quick look at the inside of that custom block. And so here I've just inputted an example part that's a torus just to give an idea of what it's doing. And then also that build plane. And with those inputs that we saw earlier, we can specify these. And what this custom block is doing is it's going through a workflow where once you've imported that part, it is changing the part to remove the interior region. So we are saying that we want to put those support structures only where we have exterior regions. And then we're looking at this angle field. So let's take a look at this angle field and probe values. And this angle field is used to kind of see where on our parts are having what angle with respect to that build plate. And this field is used then to drive where we keep points. Like if you think about that process earlier of adding multiple escape holes, this is something similar where we then filter these points using that angle field based on our criteria of whatever angle that we want to add support structures to, and then keeping those points and using those points as a basis to create our columns for the support. So this is just the support structure like you saw earlier in that file. And similarly, we also have a custom block called locations of overhang, which does this similar thing and just outputs those points as the location of overhang so that you can use this to quickly generate those points and then create your own kind of support structures as well. So let's go back to this file. So those were two custom blocks. So the first one I showed was this one. The next one I showed was an option to just create just those points. But we also have, let's turn off the visibility of this one. We also have another custom block called tapered support on a face. And what this does is it allows us to select a certain face that we want to put support structures on. So to do that, we have this filter mesh by Floodfill, which I'll explain a little bit later in the later portion of this training on meshing about how this works exactly. But this is a way for us to choose a particular face as a mesh and use that to determine our location that we want to add support to. So in this case, we're saying we're choosing this space and we want just this space to have support structures. So this custom block allows you to do that. Once we have all of these, we might think about wanting to place multiple of the same part for print. And so I'm going to show you kind of the workflow to go about doing this. So to show this, we have let's isolate this. We have, starting from that best orientation body, created, using this translate object block, a series of sphere cubes. And so it is just translating object using a vector with the sequence in Z direction, which we're saying we want 20 of. And then by using this nesting bounding box 2D nesting block, it allows us to take in the bounding box. So we brought in from this, the bounding box as input, and also brought in information about the build volume. And we're saying, let's drag this bounding box in to kind of visualize that. So we have those bounding box associated with every single one of those sphere cubes. And so now what we're saying with this nested block, or with this nesting block, is we want to organize them in a particular way based on the inputs. And if we look at this and turn on the build plane or build volume, we are saying we want to arrange them in this way onto the build plate. And so let's take a look at this, turn off that visibility. And now we have all those sphere cubes kind of rearranged on the build plate. And you can specify too how far it should be offsetted from part to part. You can add a platform offset or a perimeter offset as well. And then once you do this with that original part, it is also possible to do the same with the support structures. So in this case, I'm just going to show that initial support structures as an example of how this can be done. So that same step that we used on placing all of these volumes of these sphere cube bodies onto the build plate, we're doing the same thing with the support. And then we can slice this to export. So let's turn off the bounding box visibility. And so with the slicing of the parts to be exported out, we have in manufacturing those options. So you can go through and look at the slicing options, as well as those export blocks for different types of files. So if we look at these options, you have those export blocks that would take in the slices, and then you would specify the path and then choose the location that you want to save it to. But we have these slice on build plane, and these output then as, if we isolate it, these slices, the same thing for the supports. And then you can have these two slice data also merged together using the merge slice stacks utilities block as well, and export that. So you could also do something like slice body to black and white image stack, which would do similar thing, take in that body. And then you would specify the layer height and the X and Y image resolution and export it from there. We covered those two supports and orientations as well as slicing. So now we're going to move on to the meshing portion of the training. And to do this, I'll open up our meshing file. And we're going to use the simple example of the gyroided sphere cube to show you the different options we have in NTOP. So if we look at the most basic way to mesh something in NTOP, it would be with this mesh from implicit body block. And we can always check, and it's always good to check in the properties of whenever you're converting something into a mesh to see if the mesh is closed, it should be true. If the manifold and oriented are true, and these are good, they should be true. And also if there are any self-intersection. In this case, there are self-intersection, which is not ideal for meshing, which means that there may be some floating elements, small floating triangles that are not connected to the rest of the mesh. One way that we can more robustly mesh, instead of using this mesh from implicit body block, we have as well the option to use this mesh from implicit body by voxels block. And this is a more robust method, which allows you as well within this block to sharpen and simplify that mesh. So let's take a look at this. And if we go into that properties, we can see that with that same body input, we now have self-intersecting false. So it's not creating this these floating triangles anymore. So you also, if you turn on the option to sharpen, you see with this original block, if you don't turn on sharpen, there may be some features that are not keeping the sharpness at the edges. But if we look now at the sharpen, you can see that those edges, those sharp edges are better preserved. And then choosing simplify as well will allow the algorithm to work in a way that it would try to create the least amount of elements. And it is also possible with this block if you change the overload and choose the second option. So with these two examples, they're with the first overload. But if you choose the second overload for this block, you have the option of then also specifying a specific portion of your mesh that you want to sharpen. So here we have a box where we placed here right at the part where we have the same cube geometry. And we're saying that we want this part to, only this part to be sharpened. And if we isolate this, then it is also sharpening just that part instead of everything. So that's an option. And if you are bringing in a mesh, importing in a mesh and kind of wanting to work with that, there are a few ways to work with a mesh that if you bring in are a bit messy or need a little bit of cleanup, that these blocks can be helpful. So the first one is this split mesh. And what it does is if you have areas in the mesh where bodies aren't connected. So if you have one mesh that has different elements in different areas that aren't connected, this block can output these split mesh lists, and they are arranged in order of the biggest elements to the smallest. And you can bring these out and use these separately as well. And what this is doing here, if we input the split mesh into the filter mesh list, then we can also filter these lists based on a certain volume threshold that will allow us to see. So this mesh list 2 was dragged out into the notebook, and it is the result of this mesh that we can then use that now has those elements that are less than this volume threshold removed. And also, if you go in to see the properties of the split mesh, here I've dragged out this floating triangle. So one of these elements, this is the smallest one. And if we isolate that view and zoom to fit, we can see that there are elements like these that we have creating that self-intersection in that mesh. So these are kind of handy ways to check your mesh and work with your mesh as well to clean it up, as well as this simplify mesh by amount, which allows you to give a target amount of, so it will try to reduce the amount of elements you have based on a certain percentage that you give in, as well as mesh by threshold. So it can reduce your file size as well. Remesh surface would allow us to kind of get a more even mesh. So if we compare this mesh, isolate this one versus this remesh surface, our mesh is a lot more even, and this is good for when you have finite element analysis simulation that you want to run using meshes like this. And then if you want it to not just be a surface mesh, you would put this mesh then into a volume mesh block to convert it into a volume mesh. And then another cleanup step that's really helpful as well, especially if you're bringing in a mesh, importing it, and then you want to convert that mesh into an implicit body, but you have a mesh that is not as clean, and there are some areas that are making it so that the implicit body has some odd shapes or features, then this is a process that we would recommend for cleaning that up. And to do that is you would put in the mesh into this voxel grid from mesh block to convert it into a voxel grid, and then converting it back to a mesh by using this mesh from voxel grid. And this could help to get rid of some of the irregularities in that mesh. So once you have a mesh that you are satisfied with, you can grab any of these export mesh blocks to bring them out of NTOP. And with the export mesh block, if you go into the path folder symbol, you can look at the different options. So we have OBJ, STL, PLI, and 3MF. 3MF has its own block as well to export that out with more control options, as well as you can specifically put in a lattice, and that will export out a lattice format. And for some other features that we have for specific for meshing is we are able to choose a select area of the mesh, like I've mentioned earlier, with those support structures where we wanted to add support structures only to one particular face. And this is the block that was used for that. So how this works is we have this origin that we want to place really close to whatever face or feature that we're trying to select. And then we specify the angle. So this is kind of like a floodlight that allows us to grab onto a certain mount. So right now we have this whole face. If we play around and try to get a larger angle, then it would grab kind of more area. But this is that tool that allows us to select certain parts of a mesh. And this is very useful for when you're creating those random points from mesh as well for the different applications, like the one you've seen before with the perforations, or the ones where you create any kind of structure at different locations. In addition to this block, we also have remove mesh faces from body, where you can specify a location, for example, this block, where you want to remove, let's isolate this. So this will remove everything that is outside of this specified body, but you can also select the reverse. And let's have that run through by clicking outside of that. And then if we look at this, so this box would probably have to, if you don't want any of the surface of this structure at all on the cube, you would have to change the size, play around with that box. And so those are the options to keep anything that's inside of that volume you specify, or anything that's outside of it as well. So that's it for today's training. We've gone over a few of the different aspects and considerations that are relevant for when you are designing for additive manufacturing. If you have any questions related to this, don't hesitate to reach out. And thank you for joining today.